Alright, so now that we have introduced how GAN works intuitively, in machine learning we need to have an optimization problem, a loss function or a cost function. And when we look at the discriminator here, then you see that actually the discriminator will output either a 1 or a 0. It's nothing more than a binary classifier. And that's why we can use a binary cross-entropy as a loss function. So when intuitively what is going on? Well, basically in your classifier, this is the y equal to 1 class, and this is the y equal to 0 class. So if the image comes from the generator, it's fake. And if the image comes from this distribution, it's a good image. Alright, so what is the objective of the discriminator? It's to discriminate. So it wants to push for a probability of 1 if the data is coming from the real images. And the data is coming from P of x. And it wants to give a low score, near 0, whenever the data is generated by this generator. So that is the discriminator output, and basically you need to take the probability of that. That's basically what the discriminator will output. And here the same thing is, you will also attach a probability to it. These are exactly these two. Alright? So basically the output here, for an image coming from the generator, we should minimize. But that also means, right, if I give you 1 minus g of z, and I take the probability of this one, which is the opposite, right? Then this we can maximize. Alright? So this we can maximize, and it means exactly the same as minimizing this one. So maximizing this one or minimizing this one is exactly the same, but the nice thing we have now is we have 2 times a maximum. And this again is theta, and this is phi. Alright? So the formula of binary cross-entropy we've first seen a while ago when we discussed logistic regression. And basically your loss is difference between your reconstructed image and your real image. And that was the formula that we derived. And we've seen this formula a few times already in this course, so I'm not going to explain how we get to that. But what is interesting is that a discriminator wants to maximize discrimination. So if we have the situation where y is equal to 1, y is equal to 1 means that the image is a real image. In that case, let me call this formula 1. 1 becomes, if y is 1, then this will be 0, and this will be log reconstructed image. And the reconstructed image in our case is basically d of x. This is this one, parameterized by theta. Alright? So that is log d of x parameterized by theta. Now, if y is 0, if we see if y is 0, that means that using 1, what we have is this term will disappear, and this term will be if y is 0, this will be log of one minus, and in this case the reconstructed image is this one. Alright, so minus dg of z. Alright, and this is parameterized by theta and this by phi. Yeah? So these are the two outcomes we want to maximize. Yeah? You see, you maximize this one and maximize this one. Now if you look how this log looks like, it's a little bit like this. Yeah? So it goes to plus infinity from minus infinity, and here this point means that d of x equals 1. So if we want to maximize it, we're going to end up in 1, and that's exactly what we want. This area here is bigger than 1, so I mean that's not possible. Yeah? So we deal with probability, so the maximum we can get is here. Now if you look at the other situation, you have something like this. So you're going to end in 0, and this again is 1. Yeah? And here, if we want to find the maximum value, and sorry, this is the dx, right? And this should be d of 1 minus dg z. Alright, this is that function. And if we want to maximize this, we got to bring it to 0. Yeah? Alright? So what is the formula now that we derive? Well, I'm gonna put it over there. So what we want to do for the discriminator, no, let me put it here. For the discriminator, what we want to do is we want to find the maximum of, and then we have log d of x, yeah, plus the log of 1 minus d of g of z. Alright? So this is what we want to maximize. This is what the discriminator wants to maximize. Alright?